wait for maybe 5 minutes. Um, hope some more people join in. This is my last session. Okay. Hello. Okay, let's start. I think there's only one person. Anyway, since it's only one person, do you have any doubts? Okay, there are two. Uh, Firstly, any doubts that you have with week 12 or with previous weeks? Anything that I can clarify? Otherwise, I'll discuss questions like I normally do. So if you have any doubts, I'd like to clarify that first, then I can move on.
Previously, it was okay, but now on week 12, that is on MIMO, we can
Yeah.
continue our discussion.
Okay, fine. Okay. Anything that in this week that you want me to discuss first? Otherwise, I'll discuss some problems, but like anything from the lecture you want me to clarify?
If we can
Yeah.
revisit basic concept of entropy and how it is related
Okay.
with capacity.
Okay. Okay. Entropy and how it is related with capacity. Right. Fine. So, um, one second. So entropy is defined for any random variable. So you have x, let's say x is a random variable, and so x is a random variable, and so we have two kinds of random variables, right? We can have discrete random variable, and we can also have continuous random variables. So entropy is defined differently for both. So for discrete case, so for discrete, entropy definition is h of capital X equal to minus summation over all I pi log of pi, where I is essentially all of the values that X can take. So let's say we are talking about the tossing of a die. So I can vary from 1 to 6, right? Because you can have faces 1, 2, 3, 4, 5, 6. So you have to, and each of those faces, there can be a probability of that face appearing. So if you're talking about the random variable X, which is the face of a die, then essentially you'll have to use this formula to calculate entropy. And for continuous, you just have the continuous, you just have this like similar formula, but instead of summation, you'll have integration. That's all. So here X is a continuous random variable varying between 0 and 1 or whatever range. Let's say Gaussian variable, it's continuous random variable. So you will have to do this integration then over the, so this we all know, right? Basic probability, discrete, for discrete random variable, this is called probability mass function, PMF, and this is called probability distribution function, right? PDF. So I hope this much is clear. Now, why is this entropy? Because you can see that you can show that entropy is maximized when there is most amount of randomness or something like that. So it is actually a measure of entropy. This quantity is called entropy. In thermodynamics, also same kind of notion exists. So it's essentially it measures the extent of randomness, right? It measures the extent of randomness. So this is the basic idea of entropy. So so first maybe let's solve some, since we are discussing entropy, let's solve some assignment problems that are based only on this logic of, only on this notion of entropy, and then we can kind of move forward. Because in this assignment, I'm seeing that there is some questions that are related to entropy. So maybe let's solidify that concept first. Okay. So first question is, so similar problem is there in assignment also. Let's say we have a transmitter which is using some capital M PSK modulation, right? So we are given this, and you are told that all symbols are equiprobable. So I hope this is intuitively clear, right? Like, let's say you are throwing dice in a fair, for a fair die, all of the faces have equal probability of appearing, right? 1/6 for all of the 6 faces. So something like that. So now you are asked to calculate entropy. So you are asked, what is the entropy of source? So the source is using this modulation. What is the entropy of source? Units of this are typically bits per channel use. That's the unit of entropy. So you are asked this question. Now, how will you write you have to write a formula for this, right? So MPSK modulation, like, so that means there are these, essentially you are using M symbols, which are essentially phase shifted by 2 pi by M, something like that, right? If I remember correctly. But essentially, this is, so you have capital M discrete number of symbols as your options. So this is a discrete random variable. So that symbol that you are using, let's say, let us take BPSK. BPSK means we have either +1 or -1. So that means there are 2 symbols. And so equiprobable means that each of these symbols will appear with probability 1/2, half. So half probability that we'll get 1, half probability will get -1. So this is a discrete random variable. In general, if we make it to MPSK, we'll say with probability equiprobable. So it will be with probability 1/m. Is this clear? Because, like, as I said, example, if you take binary PSK, BPSK, so for this m equal to 2, right? So here, so for in this case, you'll basically have +1 with probability is half, and -1 with probability half. Sorry.
Hello, we cannot see your whiteboard actually.
Okay. Actually,
We are seeing only white. No, I
okay.
cannot see
Could
anything
you?
actually.
Unfortunately, so this is a problem. Can you just move up? Like, you can also kind of
No. Actually, last time that was possible, but it is not possible at this moment. You cannot. I cannot move up and down actually.
But
okay.
on my side, it is clear. I am seeing all what you are writing on the whiteboard.
But I cannot
Okay.
see.
Could you try like just swiping up and down, because I am being able to, and I think other people, you can also check. Uh, uh, okay, actually, could you follow me? Like, you can see that. I think if you just click on the following option, then you can probably do that. You are the, like, other 3 people are following me on the whiteboard. So I think for them it will be smooth. You should also
I have to
follow.
follow whiteboard.
Yeah. If you can.
I am opening, but it is written that you cannot open a whiteboard when a whiteboard is already open in meeting. This type.
Oh, okay. How about others? Is it fine?
Yes, sir. I can view.
Okay. Could you maybe just join the call, like drop out and join the call again?
Okay.
Okay, let us wait.
When we say discrete random variable,
Yeah.
Does it mean it has to be Gaussian random variable
No,
or
no, no.
any?
Gaussian is not discrete. Gaussian is continuous.
Yes.
By discrete random variable, we mean that random variable can only take discrete values. That means they cannot have so they can only take discrete values, which is, for example, let's say this Bernoulli random variable, right? You can either have 0 with probability p or 1 with probability 1 minus p. So something like that. Those are examples of discrete random variables. Or
What is the
or
formula for continuous time random variable?
so
Formula for entropy.
continuous time is a different dimension. I'm talking about continuous random variable. Continuous random variable I did mention, right? This is the formula. So Gaussian is a continuous random variable because Gaussian variable can take any value from minus infinity to plus infinity, right? It's on, whenever you plot Gaussian, you plot it like a continuous curve, right? So it can take any value. Similarly, like many other continuous random variables are there, Cauchy random variables, all of these are continuous random variables. But discrete random variable is when you can only take, let's say, a very finite set of values that are so that is a discrete random variable. When the support of that is the set of values that capital X can take, when that is finite. For example, let's say you roll a dice, then you can only have 6 values, 1, 2, 3, 4, 5, 6. You cannot have any other value, integer, non-integer, nothing. So you have exactly, so your support set is 1, 2, 3, 4, 5, 6. So that is a discrete random variable. So then, so those kind of variables are discrete. Like in communication, as I said, MPSK modulation. If you take, let's say BPSK, then you have +1 and -1. You can only take, so your constellation has only 2 symbols, right? +1, -1. And +1, -1, and then they have equal probability, so that is half. You cannot take +0.5. It is not allowed. Like you have to either send +1 or -1. So that kind of thing. So similarly, in general for MPSK, that means you will have essentially in complex plane. So this is BPSK, right? BPSK looks like +1, -1, and here 0. How does QPSK look like? QPSK is like this, and this, right? So four symbols at like kind of, it is splitting the 2 pi angle into 4 equal parts, right? So this is like 1 by √2 times 1 plus I, 1 by √2 times 1 minus I, right? So this is, so in general, MPSK will split this 2 pi angle into 2 pi by capital M parts. So that is the idea. So these are, obviously these are discrete random variables. You cannot say that I have BPSK constellation and I'll send 0. Let's say that is not allowed. You only have 2 options, either +1 or -1. So these are discrete random variables.
What is the meaning of bits per channel use? That is the unit of entropy,
Bits
as you
per
said. Channel use.
Bits per channel use. Channel use as in, if it's just as than it English suggests. One second. Are you able to follow the screen now, Mr. Bosch? Just to check. Are you able to see the screen now? And okay, bits per channel use means that every time, so for one use of the channel, that is, let's say I want to transmit some amount of data now, how many bits can I possibly send in one use of the channel? So that is entropy. So if I'm, yeah, so that is kind of the unit. And so then if you multiply it with, your transmission rate, then you will get the actual, we'll see how that maps to mutual information and capacity later. Like, I will discuss that later. First, I want to discuss a few problems regarding entropy itself. Sir, are you back? Okay, I'll
So
resume.
in BPSK, we are sending one bit or one symbol only per channel. So that means entropy is one bit. Intuitively,
No,
we can say.
no. Yeah. So I get it, but it's like you, again, it's not exactly that how much information we are sending. So mutual information is a different concept. This is actually a measure of the extent of randomness. So here, actually, we can calculate and see, but this is not exactly like that way. This is a measure of randomness. So like, if let's say, so when will randomness be zero? Randomness will be zero when we know exactly what we are sending. So let's say, for example, let's say if we are only sending +1 with probability 1, then what will be my entropy? My entropy will be this minus summation over, there's no need for summation also, summation over just 1. Then you have probability 1 log of 1, right? And this will come to be 0. So if you exactly know for sure what you are sending, then there is no randomness. So this is a measure of randomness. So the less information you have about what you are going to send, the more random it is. And so the most random you can get is when everything is equally probable. So you have no way of guessing what you are sending. So then that is when your entropy will be maximum. So this is actually, for a discrete random variable, this is actually the case when your entropy will be maximum. Does that kind of make sense? Like, can be proved and all. I'm not going into the proof part of it, but this is just intuitive argument that I'm making. That your entropy is random, your entropy is essentially a measure of how random your input is, and so yeah, that is kind of like, that is kind of the idea. So if
Okay, let us do one or two examples. I think it will be more clear.
So for this, for h of x for MPSK in general, for h of x for MPSK in general, so let us just follow the formula. If you see summation over I pi log of pi, right? Now you have m symbols, and each, for probability of each of them is 1 by m. So we can just put 1 by m and sum over I equal to 1 to m, right? Equal to minus summation I equal to 1 to capital M, 1 by m log of 1 by m, right? Now, now you can see that the summation doesn't have any component of I, it's all equal. So we can just, like, we can essentially multiply this term by capital M. So we'll have, and log of 1 by m is nothing but minus log m, right? And okay, one more important thing, we'll always take log to the base 2 over here. So for entropy and in general rate calculation later also, we'll always take log to the base 2. So when you take log to the base 2, you will use the unit bits per channel use. Otherwise, you will use nats per channel use. But that's different. Normally, don't worry about that. But yeah. So here, so what do we have? 1 by m. And as I said, log of 1 by m is minus log m. So minus and minus cancel out. Log to m. And then you are multiplying it with capital M because you are adding over m symbol. So m and m now cancel out. So your answer becomes log to m. So this is for general. This is for general case of MPSK, right? Now for BPSK, yeah. So what you said was actually right, but I thought I'll show the derivation here. For BPSK, we'll have m equal to 2. So if you put m equal to 2, what will be and what will be entropy for BPSK? You will have log of 2 to the base 2. So this is equal to 1. So you are right that, yeah, we can only send 1 bit per channel use and see that calculation also gives us the same answer. So this is the definition of entropy. Is that clear? So you
Yes,
can
it is clear.
try for anything. So let's say QPSK, you will put m equal to 4 because it's 4 PSK. So then you will get log 2 which is log of 4 to the base 2, which is 2 bits per channel use. Because you are sending one real bit and one imaginary bit. So that way, for any general MPSK, you can calculate. I hope this is clear. So this is entropy for discrete random variable, right? Now let us take continuous random variable. Yes, actually in discrete, we can also do some variation. Now, let us say you have QPSK. So for QPSK, we know m equal to 4, right? 4 PSK. And you are told that two symbols are twice as probable as the other two symbols, right? So now you are asked h of x, what is the entropy of h of x? So now the problem has changed in that now it is not equiprobable. It is not equiprobable anymore. It has like two symbols with a higher probability. So in probability class, if you remember, you have done questions on that weighted die, right? Or unfair die. So that kind of thing. So how will we solve this kind of situation, this kind of a question? So we have to essentially, again, the formula for entropy remains the same, which is minus summation I. And here I will be equal to 1 to 4 because there are 4 symbols. Pi, log of Pi, log to the base 2 of Pi. Right. Now we have to calculate these Pi's. Okay, we have to calculate these Pi's. So let us say P1 and P2, let us say these two. So we have P1, P2, P3, P4, 4 probabilities. And let us say P1 and P2 have higher probability. So the question says that two symbols are twice as probable, right? So let us say P3 equal to P4 equal to small p, right? 3 and 4 are equally probable. I'll mark the double probability one with double tick, single probability one with single tick. So P3 and P4 are equally probable. My cursor is probably visible. Okay. Then you have whatever. And then you will have P1 will be equal to P2, and this will be twice as probable as the other two. So this will be equal to 2P, right? I hope up to this it is clear. And then ultimately, you also have that summation of all these probabilities, P1 plus P2 plus P3 plus P4 has to come to 1, right? Because sum of all probabilities is equal to 1. So if you solve this, then if you put P1 equal to P2 equal to 2P, so you will have 2 into 2P plus P3 plus P3, P4 are P, so you'll have 2 into P. This is equal to 1. So if you solve, you will get P is equal to 1 by 6, if I'm not wrong. Yeah, P is equal to 1 by 6. So now you can calculate and find out that P1 is equal to P2 equal to 2P. So that is 1 by 3. And P3 equal to P4 equal to P, which is 1 by 6. Okay. And now you have to just put in the values and solve. So I hope you. So it's very simple. You just put in. So P1, P2 are the same. So we'll have 2 into 1 by 3 times log of 3 plus 2 into 1 by 6. P3 and P4 are the same. Log of 6. I'm jumping some steps, but I hope you can follow. So this is, yeah. So you can just, again, you have to use calculator and give me the answer. Okay, 2 by 3 log 3 plus 1 by 3 log 3. Plus 1 by 3 log 3 plus. So I think the answer will be 1 by 3 plus log of 3. Because log 2 is 1. If you just, so you just have to do the, you have to just put in calculator and get answer. Is this clear? Any questions? Well, I'll explain again. This is important. Okay. I hope that is good. So yeah, you can have this kind of question where it's not equally probable. So you will have to do some calculation. That is one. Now for continuous random variable, right? Now let's say you are told that you have this, you are told you have a real Gaussian variable, real Gaussian random variable, mean so with a certain, let's say mean is this yeah, so mean mean 1 and variance is also 1, let's say, right? So, and you are asked what is the, so you're told x is a real Gaussian random variable with this. So you are asked what is h of x. So if you use notation, then how do we write this? So x is a normal variable, right? Normal with mean 1 and variance 1. So that means mu, mean is 1, sigma square equal to 1. So how do we calculate this h of x? H of x is minus integration from minus infinity into infinity, probability, the probability distribution function. This is for continuous random variable. We need to know p of x for that, right? And then we will be able to do the integration. Okay. So we are told it's Gaussian random variable. So all of us, electrical engineering, we are all, I think, familiar with Gaussian. 1 over root over 2 pi sigma square e to the power minus x minus mu whole square by 2 sigma square, right? I hope everybody is familiar with this. This is the PDF of Gaussian variable. Minus infinity less than x less than infinity. So this is PDF of Gaussian random variable with mean mu. So this is basically, this is this notation, right? Mu comma sigma square. Mean mu and variance as sigma square. Now you are told that mu is 1 and sigma square is 1. Mu 1, sigma square is 1, right? You are told that. So just put in here. So P of x is equal to 1 by root 2 pi e to the power minus x minus 1 whole square by 2, right? So this is your less than x less than infinity. This is your x equal to normal 1 comma 1. Up to this, it is clear? Okay.
Is PDF and probability of X one and the same thing?
Yeah. Same. This is PDF.
Okay.
Yeah. This is just formula. This is PDF. Yeah, exactly. So now you just have to plug it in. Yeah, this is PDF. This is for entropy, for discrete function, we use probability mass function. And here for continuous variable, we are using PDF.
Okay.
Same thing. So here, eventually we'll integrate out over the whole range of x. So the specific value of x won't matter. So let us put it in here now. So we'll get 1 by root over 2 pi e to the power minus x minus 1 whole squared by 2, and then log of this thing. So log of this quantity, what will it come to be? So let us see. So we'll have firstly minus half log of 2 pi, right? From this term, we all know log, I think by now. So first term, the logs get added. And then another log will be from this e to the power minus this thing. But then we'll have to do a change of base from 2 to e and then change it back to 2. So how do we do that? So firstly, we change base to e. So minus, my bad. Yeah, minus this thing, minus half x minus 1 whole squared times. So this is when you take log of to the base e and then you change it back to 2. So you will multiply it with this thing, right? Log 2e. So you have to be a little bit careful with all of these things, with log arithmetic. You might make some small calculation errors because of this. You have to take care of change of base and all that. Dx. So now this integration you have to do. And how do we do that? Do we have to actually do the integration, or do we have other ways? Any answers? Let's see the first term. So we have one constant coming out. If we break this sum, we break this bracket. How to relate to degrees of freedom, antenna error, and resolution of the channel. We'll come to that one by one. This is we are now not talking about capacity of channels yet. This question is just on entropy. Entropy of the transmitter sending a symbol. Let's say in this case a Gaussian symbol. So we are trying to calculate how much bits per channel use we can get. So this is basic stuff. After this, we'll come to capacity and then we'll come to the formula, and there you will see. It's very simple, actually. So this part is the more complex part. Log to the base 2 pi. So again, yeah, if coming back to this, then we have this summation. If we break it up, first part is half log to the base 2 pi. Right? Do we know the value of this integral? This is nothing but a PDF, right? We are integrating a PDF over the entire range. So that answer is 1, right? If we integrate PDF over the entire range, the output will be 1. That is by basic probability. So the first term we know. For second term, we have half of log e times this thing, minus infinity to infinity, x minus 1 whole squared, right? 1 by root over 2 pi e to the power minus x minus 1 whole squared by 2 dx. This quantity. So we actually know both of these quantities. We don't have to calculate the integral. First integral is nothing but if you integrate a PDF over the whole range. So that answer is, this is 1. And by definition. And this is nothing but x integral of x minus mu whole square over the entire PDF range, right? So this is actually nothing but expectation of x minus mu whole square. By definition, this is equal to the standard deviation. This is equal to the variance, right? That is how we define variance. So this is equal to, this one is 1, and this is equal to sigma square, which is equal to, here mu is 1, remember, mu was 1. We already had defined that this is unit mu. And so sigma square is also equal to 1. That is, again, that we have taken value 1. So just if you put the values in, you will get the answer as half log of 2 pi plus half log of e. So this is your answer for entropy. And it is typically written in units of bits per channel. Sorry, there was a network issue. My whiteboard will have disappeared for a bit. Please wait. Sorry. Yeah, okay. So I hope all of you can see my whiteboard now. So okay, as I was saying that mean, so both of these are 1, and I think some part that I wrote got erased. So I'll write it again. And so yeah, then if you just put in the values, then what will you get? Half of log of 2 pi e. So that is, yeah, log 2 pi plus log e is like you can multiply. So for this bit, you have to be a little bit like used to this logarithm calculations and all that. So this is entropy of like Gaussian, one case that I took of a Gaussian random variable. You can put any mu, any sigma and solve, essentially, same idea. Okay. Okay. Right. So this is entropy again. So now that we know and we have some idea of entropy, right? So what is mutual information? Mutual information is when we uh, we know some quantity y and we are trying to estimate x. So those kind of situations is when we are trying to leverage mutual information, right? Uh, those are the conditions when we are trying to leverage mutual information. So so it comes from the very usage that, like, if I know about y, how much do you know about x? That kind of idea. So we know that this definition we know, right? Entropy definition is this thing, minus summation pi log of pi, right? So when it's x given y, then it's slightly different. Maybe let me write the continuous case formula. That is probably kind of easier to write. Px log of px, right? This is the definition of entropy for continuous case. Now, when you know something about capital Y, about a random variable capital Y, then this definition changes a little bit, right? So how does this definition change? You can all, so this is all basic information theory things that I'm kind of covering again. So first, let us say that we know some other variable capital Y has a value small y. So then what is capital? So we write it in this way, right? What is the entropy of capital X given that capital Y is equal to Y? So if you have dependent random variable, so you fix the value of the other dependent variable capital Y to be equal to some small y. And then with that fixed value, you use the conditional PDF and calculate entropy. Right? Sorry, excuse me. P of x. So this is using conditional PDF. And now if you remove the conditional, if you want to calculate in general over all y, then this integration is over x. Now you will also have to integrate over y on top of this, right? So you will now do this thing. So now you will essentially you will integrate this thing also over y. So how will you do this? So then there will be double integral p of x given capital Y equal to small y log of p of x given capital Y equal to small y, right? So this is you integrate over small x. And now this whole thing you will integrate over the probability of y itself. So you'll be integrating over p of small y and then dy. You remove this specificity by again integrating over capital Y. Okay. So this mathematics looks complicated, but that's why I showed step by step. That first you know entropy of each source or each random variable. Then for you condition on another random variable having specific value, then you integrate. And then now you want to in general find the conditional value. So you will actually no, this is wrong. I shouldn't multiply py here. It should be just dy. Okay. So now you'll also integrate over Y. Okay. So anyway, this is mutual information. And so there is this quantity, the definition of mutual information is, so mutual information between two random variables, X and Y, okay, is, so this is how you denote. So, right, mutual information between two random variables, X and Y is h of X minus h of X given Y. Or similarly, actually, for Y over X, you will define it similarly as h of Y minus h of Y given X. And this is actually, you can show this will be equal to information of X given Y. So this is a symmetrical quantity, right? So, so by mutual information, essentially you are trying to see that, let's say, okay, I know about Y. And if I know Y, then if I know the other random variable Y, then how much randomness is left in X? That is what you are trying to find out. So h of X is the total amount of randomness in X. And then if you remove the randomness after knowing Y, then you will have some amount of randomness left. So that is the kind of a measure of how much information you can send. Like if you know Y, how much information you can send using X. That is definition of mutual information. And now you are asking for capacity. So capacity is essentially, so the capacity of a channel is essentially, if you maximize over all possible, you can choose X and Y to be various different kinds of random variables, right? So if you maximize over all possibilities, then like you can choose X to be Gaussian, Y to be some binomial, whatever. So if you maximize over all permutations and combinations, what is the maximum mutual information that you can get? So that is denoted as capacity, right? So capacity is always then greater or equal to mutual information. That is by definition, because if you, the maximum mutual information is defined as capacity. Okay, any questions? Sorry. So now we can come to further things: degrees of freedom, antenna array length, resolution of channel. So all of these things come from one definition. So we cannot always do this kind of complicated calculation, like find entropy, mutual information, all of that. We don't really understand that, or it's not measurable. But thankfully, we have a better theorem to calculate this capacity, right? We have a theorem which is given by like famous Shannon theorem, which is developed by Claude Shannon from Bell Labs in 1940s. So the formula goes like this: capacity is nothing but bandwidth times log to the base 2, 1 plus SINO, signal to interference plus noise ratio. This is in bits per second. So this is the formula for capacity that is used. Right. Is this clear? Because normally you will be dealing with directly this formula. You won't be like going to the absolute fundamentals of computing mutual information and all of that. You will just be, as electrical engineers, will typically be using the Shannon formula directly. Right. Now, those proofs for MIMO channels are there. I can show them, but it's kind of involved and doesn't make sense. You can see it from the lectures. But for a general MIMO channel, so what do you have in a MIMO channel? In a MIMO channel, you have a transmitter, right? With 1, 2, and so on and so forth. Let's say you have a transmitter with NT antennas, and you have a receiver, let's say, yeah, smaller receiver. I'm just drawing, like, it's not necessary that receiver is too smaller than transmitter. So you have NR antenna, that receiver. NR antennas. So this is transmitter, this is receiver, TXRX. In this case, you have NT greater than NR. You can also have it reverse, right? So, okay. So it can be shown that like this general for MIMO channel capacity is, if I divide by bandwidth, I'm dividing by bandwidth for simplicity. Now what happens is each of these antennas, like there is this notion of rank of a channel, right? So how many streams can I send in parallel? That is determined by the rank of the channel. So if I assume that like, so here firstly, what will be the channel dimension in MIMO? So you have NR antennas. So you have one channel for each of these parts, right? So this will be H11. This will be H12. This will be H1 capital NT. This is for the first one. Similarly, this will be H21, H22, and so on. So you will have one capital H matrix. This is your channel matrix, whose dimensions are NR cross NT. And in this case, so if you assume full rank, that is, there is very little correlation between the channels, and so you are getting the maximum possible, spatial diversity, maximum possible spread, or the maximum possible distinction. So for full rank, the capacity is actually equal to something like this: n min log of 1 plus SINR, right? Where n min is nothing but minimum of NT, comma NR. I can derive this, but then it's beyond the point. So this is the formula for capacity. Like, let's say you have something like NT cross NR, right? So you typically, like, let's say if somebody says 8 cross 2 MIMO, 8 cross 2 MIMO, so that means NR is 8 and NT is equal to 2. So what is minimum between 8 and 2? 8 and 2 minimum is 2, right? So you can send 2 streams in parallel, and that is why you have this multiplying factor. Because what happens between, 1 second, I think I zoom, yeah. Sorry for that. What happens if you have parallel channels, then you can just add their capacities, and then all of the channels are similar. So you will just keep on adding. So, so this, you can show that this formula holds, that capacity is n min times log of 1 plus SNR, where n min is minimum of these two, right? So this is how it relates to degrees of freedom and antenna array length channel. First two is at least clear, right? Degrees of freedom is essentially how many channels, how many layers in 3GPP terminology, or how many parallel streams you can send. So that is given by Nmin, which is minimum of NT, NR. Where NT, NR are, as you can see, NT is the number of antennas in transmitter, number of antennas in receiver is NR, and that is related to antenna array length, right? Like if you know the antenna spacing, we know that if we have to have minimum antenna correlation, then antenna spacing has to be lambda by. And let's say array length is LT. Then what will be NT? NT will be LT divided by lambda by 2. So you can do this calculation to LT by lambda, where lambda is whatever wavelength you are using to transmit. So you can kind of calculate as to maximum how many antennas you can fit in a certain length. So that you can do. Anyway, so there is one assignment question that relates to this formula itself. So just I thought I'll touch upon it. So when SINR, again I'll write the formula for clarity. C by B equal to N min log of 1 plus SINR, right? Signal to interference plus noise ratio, right? So let's say SINR is high. So if SINR is high, what will happen? Then essentially, then you will have 1 plus SINR is approximately equal to SINR because 1 will be much smaller. So then your C by V, your capacity per unit bandwidth, is approximately equal to N min log of SINR. So you can use this approximate formula to derive any conclusion. So this is for high SINR. Now for I'll just type high SINR. This is the formula. Now for low SINR, we have this formula, right? That log, my bad, this slightly corrected. So we have this function like ln of 1 plus x is approximately equal to x for small x. For small x, where ln is log to the base e, natural logarithm, right? This identity exists from limits from calculus, we know log to the base e. And now what we have here is, if for low SNR, for very low SNR, we have log to the base 2. So we can do change of base. We can change it to log to the base e and then multiply with log of 2 to the base e, right? Log of e to the base 2. So C by B is now, like if I do change of base, N min log of e 1 plus SINR times log of e to the base 2, right? Just doing change of base. And then this approximately is equal to SINR. So that is why N min SINR times log of e. You get this formula. Okay, so this is low SNR approximation. Low SNR and high SNR approximations, right? You can use these kind of notions. What else? I hope this is clear. Any questions? Otherwise, I'll move on. Okay. What else? So this was question 1 on entropy. This is discrete time. This is continuous time. I'll call this question 2. And for MIMO channel capacity, this is question 3. So, and this is, I think, the last question in your assignment. You can use these facts and answer that approximately for high SNR, this is the formula. For low SNR, this is the formula. So, this you can answer. Okay. Now let us see.
What is the meaning of Hermitian operator?
Okay, we'll come to that. Hermitian is not very simple. So H is channels are typically complex random matrices in this case. So H Hermitian. So we do know this one, right? H transpose we know, right? How to take transpose of a matrix. You just make rows into columns, right? And then on top of this, if you take conjugate, so what you will get is H Hermitian. By conjugate, what do you mean? By conjugate, you mean that A plus IB for a complex number conjugate becomes A minus IB, and so on and so forth, right? Or if you write it in polar form, then you will have A to the power J theta conjugate will become capital A e to the power minus J theta. That magnitude remains the same. The angle changes its direction. So if you take conjugate of a transpose, what you will get is Hermitian. Is that clear or any doubt?
Okay, that's fine.
Okay. Fine. So then 100% good. And another notion that I kind of discussed in passing is rank of a matrix. So this comes from linear algebra, right? So as I said, that you have MIMO, NR cross NT MIMO, right? NR receive antennas, NT transmit antennas. And you are told NT less than NR. Just as an example, you have less transmit antennas and receive antenna. And you are told channel is full rank. So you are asked what is the rank of channel H? So the answer for this is whatever is smaller. So rank of channel H, answer for this is actually N min, which is equal to, it is always minimum of NT comma NR. Rank, as we know, is essentially the number of independent streams that we can send over the channel, or the maximum number of independent streams that we can send over the channel. So that is always whatever is minimum between NT and NR, right? So if in this case you are given NT less than NR, so that means this minimum will come out to be NT, right? I hope this is clear. Then you have another notion of SVD. does multipath affect the degree of freedom? We'll come to that. 1 second. So I need to cover this before I get to that question. Singular value decomposition. Right? So what do you mean by SVD? In MATLAB, there is this routine SVD which does the calculation for us. But essentially, it is, so let's say we have channel matrix N H, which is always NR cross NT. So this can, in singular value decomposition, we'll divide it into three matrices actually, U sigma V Hermitian, where this is the precoding matrix VH. So V Hermitian, yeah, so this is typically NT cross NT. This one is NR cross NT. And this is NR cross NR. So typically this U and V are the unitary matrices. And sigma is diagonal matrix. Sigma is diagonal, but not strictly diagonal. So as you can see that V and U are both square matrices, right? And by unitary matrix, what I mean is this thing, that like U Hermitian U equal to I and so U Hermitian U will be equal to I equal to U Hermitian, and similarly V Hermitian V is equal to I equal to V Hermitian. So what happens is all of the columns and rows are orthogonal to each other. The columns are orthogonal to each other. Right? And then the sigma matrix is, I'll put it as quote unquote diagonal, because you can see that normally diagonal matrix is square matrix, but this is not square. This is NR cross NT, and it will, in general, we won't have NR equal to NT, right? So this will be a rectangular matrix. And so this will essentially have something like some part it will be non-zero, right? Some part it will be non-zero. So this will be sigma 1 till some sigma t, whatever. And then rest part here and here, it will be zero padding, so that the dimensions are matched. So either here or here, there will be zero padding, wherever it is needed. So if NR is greater than NT, we see that there are more columns than rows. So to fill that space, because this is NR cross NT, so number of columns is NT, number of rows is higher. So that means there will be some space down which is filled with zero. And so this is for NR less than NT. So this is how sigma looks like when NR is less than NT. And when NR is greater than NT, and when NR is less than NT, then we have a different look, right? Because then number of columns is smaller. Number of rows is smaller. Here number of columns is smaller. So we are adding rows. Here number of rows is smaller. So we'll have sigma 1 till sigma. Here, let me write it as sigma NT. Assuming full rank matrix again. Sigma NT. Here it is sigma 1 to sigma NR. Just diagonal matrix with 0 here, 0 here, 0 here, 0 here. And then after this, there is a zero padding. Now, what is the length of each of these zero paddings? In this case, length is whatever is remaining, right? NT rows are done, NR minus NT rows are left. So NR minus NT cross the number of columns, which is NT. And here the zero padding is instead NR cross NT minus NR. right? Because essentially we are just doing zero padding so that the matrix multiplication is valid. 0 NR cross NT minus NR. So this is for NR less than NT. So these are the two formulas. So this is how you do singular value decomposition of a channel. So you're trying to essentially separate the channel into independent streams, right? Separate the channel into independent streams. Now, to coming back to your question, Beula, multipath. What multipath does is it multipath. Multipath essentially introduces something known as correlations between the channel coefficients. So here in the formula that we wrote for capital sigma, so this also relates to one of your assignment questions. You can see question 11. This notion is there. So when there are correlations, then what happens is H is no longer full rank. So our assumption typically fails. Because what happens when multipath happens is then there are reflections and all of this. So signals start to like combine with each other, and this all of those things happen. So then your channel is no longer full rank. You have some correlations introduced in the channel. So your rank then will be essentially your rank will become less than n-min, where n-min is minimum of nt comma nr. So multipath can have a negative effect on the degrees of freedom. Yes. I hope this is clear. What else? Any other questions? Then there is this notion of log debt capacity. So again, I'm not going to go through the derivation, but there is this form, question 5, I believe. Like in assignment, it is question number 12 and 13, right? It is both based on the same concept, so I'll cover. Question 6. So you're asked what is log debt capacity? Log debt stands for determinant capacity of channel capital H. So this actually has two formulae. C by B equal to expectation of log. We are taking expectation because we are calculating ergodic capacity. Log of determinant I of NR. Channel H is NR cross NT. Agree? I of NR plus this thing plus power, signal power by noise power E by N naught H emission. So this is one formula. Now you have to be careful that you are writing H emission or H emission H. You can quickly check using dimensionality analysis. This is identity NR. So this is NR cross NR. Let us see. H is NR cross NT and H emission is conjugate transpose, so NT cross NR. So this is also NR cross NR, which take transpose of whole system of the whole matrix, then determinant does not change. So if we take transpose, or like essentially we can prove this. So this is equal to this also. You can also write it this way. H Hermitian H. So then this becomes that and that so then this becomes NT cross NR, right? Because H Hermitian you are taking. H Hermitian you are taking. So this whole thing becomes NT cross NR times NR cross NT. So this becomes NT cross NT, which is same dimension as this. Now, which formula should we use? Now this depends on relative values of NR and NT. So how do we determine that? How do we determine that? So if we typically judge by the, like we want to be computationally efficient, right? So the larger the matrix, the more the time it will take to calculate determinants. Computational computation. So we want to have less computational complexity. So there can be two cases, right? We can have NR greater than NT. That is one case, and then NT greater than NR is the second case. NT greater than NR is the second case. So when NR is greater than NT, then we should be using formula number 2. Then we should be using formula number 2 because NT is smaller, so this determinant will be executed faster, right? This is because determinant 2 is faster. And similarly, if NT is greater than NR, then NR is smaller. That means we should use formula 1 because determinant 1 is faster. Okay. I hope this makes sense. Like, so depending on if NR greater than NT, then you will give the second formula as answer. Then if NT greater than NR, you will give the first formula as answer. Because the logic is essentially this: the computation complexity has to be reduced. So this, I hope this is clear. If you like, I don't want to do the derivation all over again. It's there in the lecture. I just conceptually wanted to give an idea. With this, I think I don't have more to cover. That is all that was there. And then rest is very simple from straight from lecture. So there's nothing new. Model question for final test. I don't have it. I am not involved with setting the final test or any model questions. If the instructor, if Professor David wants to provide, he will provide to his PAs. You can request it on the platform, on the online forum. But yeah, as I said, I'm not involved with any of those decisions, or my job is done. So yeah, I'm not involved with that. Anything else? Otherwise, I will end the session. Thank you all for attending. Okay. Good luck for the final exam.
Thank you. Thank you very much.